Today we are going to do laser under atomic molecular physics. So first we'll go through some very basic expressions in laser and then we'll do a few problems. So let us get started. So suppose we have a two-level system, 1 and 2, then we know we can define Einstein coefficients, B12 stimulated absorption, this is stimulated emission from 2 to 1, and this is spontaneous emission rate from 2 to 1. Then under conditions of thermal equilibrium, this B21 is equal to B12, and the ratios of the spontaneous emission rate and stimulated emission rate is dependent on the resonant frequency between 1 and 2, which is given by nu. So this ratio is 8 pi h nu cubed by c cubed. Then we come to optical activity, optical cavity. So optical cavity, to make a laser we need optical cavity, and the frequencies that are supported in that optical cavity of length L are given by nu n is equal to nc, where n is here a number, integer number, and c is the velocity of light, mu is the refractive index of that optical cavity, and L is the length of the optical cavity. So these are the frequencies that can be excited in that optical cavity. So optical cavity consists of reflecting mirrors at both ends, and so the spacing between these frequencies is given by delta nu. This is C divided by twice mu L. And in optical cavity we have this concept of spectral width. So you won't get a very sharp line, but there will be a spread in the frequency of these frequencies nu n, that is given by 1 over 2 pi Tc. So this is the expression for spectral width. And what is Tc? Tc is the survival time of a photon survival time, and that is an expression which is minus delta nu. So this is delta nu ln 1 minus x whole to the power minus 1, and x is related to the reflectivities of the mirrors which are there on both sides of the optical cavity. So R1 and R2 are the reflectivities of the mirror, and this R1 and R2 is the reflectivities of the mirror, and alpha is the absorption coefficient. So these all represent the losses. Alpha represents the loss of radiation inside the cavity, and if R1 and R2 are 1, then from reflection there is no loss, but in general in one case R1 will be very close to 1, and in the other case R2 will be slightly less than 1 to get the output from the laser. Okay, so this is a typical mode versus energy gain inside optical cavity. So this is the loop gain in the y-axis, and this is the frequencies which are excited in the optical cavity. Those are given by this blue lines, and you can see loop gain is the gain in the intensity of the radiation when it travels one loop inside the one complete, when it goes around the optical cavity once. This is the gain in the intensity of the radiation. So that is loop gain. So you can see that in this green stripe represents the region or the frequencies. So these frequencies are like these frequencies which lie between these two lines are the frequencies for which the loop gain is greater than 1. Other than that, all the frequencies have loop gain 1 or less than 1. So the frequencies represented by the stripes are the frequencies which are suitable for laser light. Okay, and you can see this is the distance between modes, and this is going to be c by 2 mu l. We have done this before. And there is a Doppler shift in a laser, that is shift in the line, spectral line, because the atom or molecule is not static but it is continuously moving. It's continuously moving here and there. So because of that, there will be a Doppler shift in the frequency, and that is dependent on the temperature through this expression. Mu0 is the frequency that we would observe if the atom were static, but since the atom is not static and it's how fast it moves depends on the temperature on an average, so this delta nu depends on temperature through this expression. Let us change the color to blue. So we'll do a problem. So calculate the omega for transition 2p to 1s in the hydrogen. It is given that the spontaneous emission lifetime of the 2p state is 1.6 nanosecond. Calculate the B coefficient. So the answer is omega is 1.5 into 10 to the 16 hertz and B21 is 2.5 into 10 to the power 19. This is per second. So first, omega, how can you calculate? 2p to 1s transition is basically a transition from the state having energy minus 3.4 electron volt to the state minus 13.6 electron volt. So from here, H cross omega is equal to the change in energy, and we can calculate omega. And B21 is given, A21 is given. A21 is times the time lifetime of the spontaneous emission is given 1.6 nanosecond. So the spontaneous emission rate is actually 1 by tau, that is A21. So from here I can calculate A21. So once I know A21, I can calculate B21 from the relation the relation between the Einstein coefficients, which we have already discussed. Go to the next problem. The energies of three lowest states of an atom are E0, E1 and E2. E0 is minus 14, E1 is minus 9 and E2 is minus 7 in electron volt. The Einstein coefficients are A10 is equal to 3 into 10 to the power 8 per second, A20 1.2 into 10 to the power 8 per second, and A21 8 into 10 to the power 7 per second. If a large number of atoms are in level energy 2, the mean radiative lifetime is how many seconds? So this you can easily calculate. So we have three levels. This is 2, this is 1 and this is 0. So this is 2, this is 1 and this is 0. So dN2 dt is spontaneous change from 2 to 1 and 2 to 0. So that is minus A21 N2 minus A20 N2. So from here we can easily check that N2 will have a form of n2 is equal to e to the minus t by tau, and tau is the mean lifetime. Tau is 1 over A21 plus A20, and A21 and A20 are given. So from here you can calculate the mean radiative lifetime, which is tau. The separation between the energy levels of a two-level atom is 2 electron volt. Suppose that 4 into 10 to the power 20 are in the ground state, and 7 into 10 to the power 20 atoms are pumped in the excited state just before lasing starts. Show that the energy released in a single pulse is 448 joules. So initially we have this many atoms in the state 2 and we have this many atoms in state 1. So what happens when this lasing stops? So now lasing starts. The lasing will stop as soon as n2 minus n1 by 2 number of atoms from state 2 will reach state 1. That is, the population of n1 will increase by n2 minus n1 by 2, and the population of n2 will decrease by n2 minus n1 by 2, and then both of them will have the same population, and that will be n2 plus n1 by 2, and when this is achieved, the lasing stops, and that is how you will get a single pulse. So the amount of energy will be in that single pulse will be n2 minus n1 by 2 into h nu. This is the pulse energy, and if you calculate, it comes out to be 48 joules. So the volume of an optical cavity is 1 centimeter cubed. Show that the number of modes it can support within a bandwidth of 0.1 nanometer centered at lambda is equal to 500 nanometer is around 4 into 10 to the power 10. So the number of modes between this in this bandwidth of 0.1 nanometer centered at lambda is equal to 500 nanometer is around 4 into 10 to the power 10. This is what we have to show. So we know that in optical cavity we have reflected rays. So if you consider reflection along, say, in the x direction, then twice kx into L is equal to 2n pi. So this condition has to be satisfied for reflection. So for ky and kz we can write similar relations. So the volume for each k that is supported by the optical cavity is pi by L whole cubed. So number of modes will be d3k. So d3k is a small volume in the k space, and volume of each k is delta v. So there will be d3k by delta v number of k's in d3k, and you have to multiply it by 2 because for each k there will be 2 transverse modes, independent transverse modes you can say, or 2 polarizations, and then we have to divide this whole thing by 8 because we are considering only, say, k in the positive direction. So kx is positive, ky is positive, and kz is positive, since we are considering reflection. So we can say that we are only in the first quadrant and divide by 8, and if we do this, then d3k we can write it as 4 pi k square dk. This we can write d3k like this in spherical polar coordinates, delta v, and this is twice. So these things remain the same. And now from K to we convert things to lambda using this relation. K is equal to 2 pi by lambda, magnitude of K, and from there we get this relation. So V is the volume, which is here 1 centimeter cubed, and from there we can calculate. So this will give us 4 into almost 4 into 10 to the power 10 modes in that optical cavity of volume 1 centimeter cubed. So a gas laser has been designed to operate at lambda is equal to 0.5 micrometer with a cavity of 1 meter. This is the length of the cavity. With this setup, the frequency is found to be larger than the desired frequency by 100 Hertz. Okay, so the frequency is found to be larger than the frequency that we want by 100 Hertz. So we use the expression for the frequency that are generated in an optical cavity, NC by 2 mu L. So delta nu is equal to minus NC by 2 mu L square into dl. Or from here I can calculate dl, because the desired frequency here the frequency is found to be larger than the desired frequency by 100 Hertz. So the length has to be changed. So desired frequency is, so we have to decrease the frequency. So delta mu has to be, this is negative minus 100. So the dl will be positive. So we can find out dl. A two-level system in a thermal blackbody environment can decay from the excited state by both spontaneous and stimulated emission. Show that at room temperature, that is 300 degree Kelvin, the frequency below which stimulated emission dominates over spontaneous emission is around 10 to the power 13 Hertz. So rate of stimulated emission, rate of spontaneous emission is equal to B21 into U nu. U nu is the energy density per unit frequency. So B21 into U nu is the rate of stimulated emission, and the rate of spontaneous emission is proportional to 8 to 1. So this is the ratio, has to be greater than 1 for stimulated emission to be dominant. And U nu is actually this expression, Planck's law. And we know the relation between, what is the relation between? We know the relation between B21 divided by 8 to 1. That we have already done in the beginning. And so from there we can get the frequency. So in which stimulated emission dominates over the spontaneous emission. This is around 10 to the. So from here we have to calculate, we just put it here, and from there we have to calculate the nu. So consider, we go next problem. Consider the helium neon laser cavity consisting of two mirrors of reflectivities R1 is equal to 1 and R2 is equal to 0.98. The mirrors are separated by D is equal to 20 centimeters, and the medium in between has a refractive index of 1 and absorption coefficient alpha is equal to 0. The value of separation between the nodes delta nu and the width delta nu p of each mode are, we have to find out values. So this is easy. So delta nu, we had already, the distance between the frequencies is c by 2 mu L. So mu is 1, L is given, and so we can find out this delta nu directly. And delta nu p we have already done is 1 by 2 pi Tc. And what is Tc? Tc is equal to 1 by delta nu ln 1 minus x, where x is 1 minus r1 r2 is twice alpha L. So r1 is given there, r2 is given, alpha is 0, and from there we can find Tc. Delta nu is given, we have already found out. So from here we can find out the width of each mode, delta nu p. So consider the energy level diagram for the molecular nitrogen laser. This is the next problem. The pump rate is R is equal to 10 to the power 20 atoms per centimeter cube per second, and the characteristic decay times are tau to 1 is equal to 20 nanosecond and tau 1 is equal to 1 if tau 1 is equal to 1 microsecond. Show that the equilibrium population of level 1, that is, which is n1, is 10 to the power 14 centimeter, 10 to the 14 per centimeter cubed. So this is this picture. So this is 0, 1, 2, 3 levels. So the characteristic time of decay tau to 1 is given, and from 2 to 1 and from 1 to 0 tau 1 is given. So we have to find out what is n1. So dn to dt is r minus n2 1 by tau to 1. So 1 by tau to 1 is the rate of transition from 2 to 1. Okay, so this gives, and dn1 dt is equal to n2 tau to 1. So this is the rate at which from here atoms are changing to level to energy, from level 2 to level 1. This is this, and then from 1 to 0 there is a change, so that is given by this term minus n1 by tau 1. 1 by tau 1 is the rate of transition from 1 to 0. Now for equilibrium, dn1 dt is 0 and dn2 dt is equal to 0. So we can calculate n2 from this expression, and once we have calculated n2 from this expression, we can calculate n1. So we'll stop here and we'll soon meet with the next series. Thank you.